All right, so we've talked about the idea of magnetic flux, and basically Faraday's law tells us why we care about the magnetic flux. So we care about the magnetic flux because when you change the magnetic flux through some loop, it's going to induce an electromotive force, which will then drive a current around the loop. So up until now, we've talked about when we've driven a current, we've talked about driving a current by providing a potential difference through a battery. What we do through Faraday's law is we can now say I don't actually need a battery to drive a current. What I need to do is change the magnetic flux through my loop. That will also drive a current. So this gives us a second way to drive a current around the loop. Again, electromotive force, EMF, is what we'll usually call it rather than saying electromotive force over and over and over again. But the EMF is really mislabeled. It's not a force at all. Really what it is it's a potential difference. So in the same way that a battery provides a potential difference, an EMF provides a potential difference. In this context, it's simply going to be an induced potential difference. So from what we learned about the magnetic flux, we said there are three ways that you can change the magnetic flux through a loop. You can either change the strength of the magnetic field, make it stronger, make it weaker. You can change the area of the loop. You can either do this by literally changing the area of the loop, making it bigger, making it smaller, or you can change the area of the loop that's in the field. So one of the ways that we'll see that we can induce an EMF is take a loop but pull it into or out of a magnetic field. So the amount of area of the loop that's in the field is changing. And then the third option is we can change the relative orientation of the magnetic field in the loop. So if I start to twist my loop about in the magnetic field, that will also induce an EMF. So these are the three ways that we can induce an EMF. Mathematically, Faraday's law looks like this. So Faraday's law of mathematic induction tells us that the induced EMF is going to be equal to the negative sign is in the equation, but we'll actually almost always end up dealing with the absolute value of the EMF and deal with the minus sign through what's known as Lenz's law. And Lenz's law is just going to give us a right-hand rule. But it says that the induced EMF is equal to, there's a minus sign in here. N is the number of loops. So if I've got some sort of device that's made up of 5 loops or 10 loops or 100 loops, that's going to be my N. And then what I'm interested in is how the magnetic flux changes over time. And so again, we know how to calculate this for a flat surface in a constant field. And so this is the way that we're going to deal with magnetic inductions. We're going to say, well, if we put a flat surface in a constant field, or a flat surface provided by a loop around which current can flow, we're going to put that in a magnetic field. That magnetic field will be constant in space, and then we'll let things change in time. And so this means that there are three ways that I can induce an EMF, and part of what we're going to do is have to identify what it is that's changing in the problem. So are we changing the magnetic field? Are we changing the area of the loop that's in the magnetic field? Or are we changing the relative orientation between those two things? So this is sort of going to be in terms of functionally working with Faraday's law. Mostly what we're going to do is emphasize, well, which of these three things is changing? Because that's going to tell us what we need to do mathematically. So as an example, here I've got a situation where I'm changing a magnetic field. So let's say I've got a current loop sitting in a constant magnetic field, and I can simply increase or decrease based on how I sort of choose to set up this electromagnet. So I can increase the magnetic field if I wanted to, or I could decrease the magnetic field if I wanted to. Similarly, here's a loop, and I can take a magnet, and I can take this bar magnet and either move it towards the loop or away from the loop. Obviously, as I move the bar magnet towards the loop, I'm increasing the magnetic flux because I have a stronger magnetic field that's close to the loop now. If I pull the bar magnet away, I'm decreasing the strength of the magnetic field through the loop. So both of these are options for how I can change the magnetic field. If I'm changing the magnetic field, then that's going to stay inside my delta B term, and everything else I can bring out. I can also change the area of the loop that's in the field. So here's a situation where I've basically got a rail, and then I've got a conductor that lies across it. And again, as I start to move that conductor, if there's a magnetic field, I'm changing the area within this loop that's made by three sides of the rail plus the conductor. So if I were to pull this conductor away, I would be increasing the area. Here's a situation where I'm not physically changing the area. Right here, I literally physically changed the area. It got bigger as I pulled this away. Here I'm not literally changing the area of my loop. What I am doing is changing the amount of that loop that's in the magnetic field, the amount of that area that is being penetrated by magnetic field lines. And so here, as I pull my loop out of the magnetic field, I'm decreasing the area that receives magnetic flux. So this would be a situation where the B and the cosine phi term, those would be constant, so we could pull those out of the delta, and I'd be left with delta A over delta T. So what's the change in area over the change in time? And then my third option is, well, I can change the relative orientation. And this is actually functionally fairly important because this is how motors work. But basically what I'm doing here is I can take my loop, set it in a magnetic field. I can keep the area of the loop constant. I can keep the magnetic field constant. But what I'm doing is I'm changing the relative orientation. So as I rotate this loop around, I'm changing the angle between the area vector for the loop and the magnetic field. So this would be a situation where the B and A could now come out, and I'd be left with how that orientation is changing with respect to time. So these are the three options I've got in terms of changing the magnetic flux. And so when we go to work Faraday's law problems, we'll pay attention to which of these three is changing so we know what needs to stay inside the delta term, and everything else can then be pulled out.